This is part 2 of our week 6 materials, which is covering chapter 27. And I'm going to start talking about RC circuits now. An RC circuit just contains a resistor and a capacitor like this. Now, if the switch is open at A, what that means is the switch here is moved to this position here. Charge begins to flow, so charge flows like this, and the capacitor starts charging. Once VC, so the potential of the capacitor, is equal to V battery here, the current stops flowing. Now, according to Kirchhoff's loop rule, if we go around in this circle here, E, our electromotive force, minus Q over C, which is the potential difference across this, minus I times R is equal to 0. So here we have our gain in potential, drop in potential, drop in potential, and they have to be equal to 0 like this. Now, when charge or current is changing in time, instead of saying capital Q, we're just going to say little q. Instead of capital I, we go with little I. Now, I initial though, so right when we flip the switch here, there's going to be a current that starts flowing. And right at that point in time, the current is equal to E divided by R. So this is what it looks like initially. But then when the capacitor is charged to its max, Q max, I final, our final current is going to be 0. So once this is fully charged, no more current is flowing through there. We also know that Q max is equal to C times E, where this is just the electromotive force here. So then what is the time dependence of the charge or current? So how does this current change in time? Because we know it goes from this and it ends up as this, but like what's the intermediate process? Well, we know that I is equal to dq over dt, so we're going to plug that into this equation here and just divide it by r. And we see that we get dq over dt is equal to this. All I'm going to do, multiply the top and bottom by c, put them all into some nice equation here, so we get dq over dt is equal to this. The next thing we do is we take everything that has to do with q and we put it onto this side of the equation. Everything that has to do with not q to the other. So it looks like this. dq over q minus ce is equal to negative 1 over rc dt. We're going to take the integral from both sides. So we integrate from 0 to q, dq q minus ce. Because remember, we start with no charge. And well, at some point in time, we're going to have charge q on the capacitor. It's equal to integral from 0 to time t, negative 1 over rc dt. We're going to solve this, and we get this here. ln q minus ce divided by negative ce, and this is equal to negative t over rc. Now the next thing we're going to do is do e to the power of on both sides, and that's going to get us get rid of this ln here that we don't want. So then all we have on this side is q minus ce divided by negative ce is equal to e to the power of negative t over rc. We're going to move everything that's not q to the other side, and we get this equation here. So Q being how much charge do we have on the capacitor, we know it changes with time. It changes with time via this equation. So C, the capacitance, times our electromotive force, 1 minus e to the negative t over rc. We also know that this here, this is Q max. So we can write it as such. And we also know that I is equal to dq over dt. So then all we have to do is take the time derivative of this and we figure out what the current is at any moment in time. So at any moment in time t, the current flowing through our system is equal to this. Now remember that the charge starts off at 0 at time is equal to 0. And it ends up with Q max is equal to CE. And that is actually what this equation is telling us here. It's saying that as t approaches infinity, Q max is CE. So essentially we get Q of t is equal to Q max when time goes to infinity. On the other hand, the current, it starts off with this value here, and we see that value in the equation. That's its initial value, and then it decreases as e to the negative t over rc. So that means as time approaches infinity, this approaches 0. So our current goes to 0. Now we're going to do one more thing where we replace RC by tau, where tau is defined to be the time constant. And that's just the time over which the current decreases by 1 over e of its original value. That's not super important. What is important is just knowing that this is just R times C, and we're just plugging it in because it makes some things look a little bit prettier when we graph them. So here, this is tau, that is tau, that is tau. Now this is what happens when we charge our capacitor, right? But what happens when we discharge our capacitor? Well, essentially it's going to be the opposite, but we can express that mathematically. So we're going to start off with the capacitor being fully charged, and that means initially delta V is equal to Q divided by C. At this point, there is no potential difference across R because there is no current. So if we go back up here, when this is fully charged, there is no current flowing here. So then, if the switch was moved to B, the capacitor starts discharging through the resistor. So here, if we switch it like this is our circuit instead. We're not going through the battery anymore, we're just going through the resistor and the capacitor. Now, according to the loop rule, we know that this is our capacitor and then this is our resistor. So negative Q over C minus IR is equal to 0. Now we know that I is equal to dQ over dt, so all we're going to do is insert that into this equation here like we've done before and put it onto the other side, and then we get negative R dQ over dt, because literally all I did was that is equal to Q over C. All we do again is put everything that has a Q on one side, so dQ and Q on one side of the equation, R, dt, and C on the other side of the equation. And we're integrating here where we start off at Qi, some maximum value of Q, and we're going all the way till some point where we have charge Q on the capacitor. We have that, and then on this right side, we're going from time is equal to 0 to time t. Solve the integral again, and we get this. We do the same thing, e to the power of ln, e to the power of this, and we get Q of t is equal to Qi e to the negative t over Rc. Remember, Rc is tau, so this here is tau here. Now we also know that I of t is just dq over dt, take the time derivative, and we get this. So what we see is that we can plot these, and when we have originally this situation here where we have this switch is going to be attached here, so the current goes like this, we get a charging of the capacitor. And we've seen that these are our two equations for when we're charging. So again, we start off at this point here, and then Q increases until it's at a maximum. The current starts off at a maximum, decreases until it's 0. And we've seen those in those equations. On the other hand, when we flip the switch here, we have discharging happening. And essentially, it's literally these plots, but backwards. So we start off with no current, and then we increase the current as it discharges. And we have the equations here, Q of t and I of t.